The topic is applied optimization, and if you're following along in the Thomas Calculus textbook, this corresponds to section 4.6. Applied optimization is really just an application of something we did earlier in the chapter. If you recall, at the very beginning of the chapter, we learned about the concept of an absolute min and absolute max, and the extreme value theorem. Specifically, the extreme value theorem said that if we have a continuous function on a closed and bounded interval, the function does attain a min and a max. Then when we learned about the idea of critical numbers, we discovered that we could find the min and max by checking we could find the min and the max by checking a very small subset of the points on the interval. Specifically, just check the critical numbers and the endpoints. So, in fact, I've put up here right below the example of that, which is we see on the left. We have a continuous function on the closed interval AB, and in blue, what you see is the procedure for finding the absolute min and max on that function on that interval. So on the right, what I have is another example of a function that does have a max. We can see that this function, in fact, does have a max, even though the interval on which that function is defined is actually not closed. It's not closed and it's not bounded. It's the open interval. Actually, I'll leave open the question of whether it's open when it includes infinity, but the point is it's not a closed interval and it's not a bounded interval. So that theorem, the extreme value theorem, doesn't apply, and yet in some cases we might be able to find a max or a min anyway, even though its existence is not guaranteed by the extreme value theorem. So the, the the idea of this section, I'm just going to give you sort of the 5-second summary of what this is about. Let's suppose that instead of just a purely abstract mathematical function, let's say that that function represents some physical phenomenon that we'd like to do really well or maybe really poorly. It represents, for example, the area of an enclosure, and maybe we'd like to find the largest possible area, or maybe it represents the cost of manufacturing something. Excuse me, and we'd like to manufacture that thing for as little money as possible. So if the function represents some phenomenon that we care about, what we can do is we can find the point at which the min or the max, whichever one we're looking for, occurs. And what that's going to give us is the way to do this thing as well or as poorly as it can possibly be done. If we simply assume that the best way you can do it achieves the max, the worst way you can do it achieves the min, although sometimes, depending on what you care about, those senses might be flipped. Either way, once you find the location of that max and min, you now have the best way of performing that process. So essentially what we're going to do in this section is we're going to read a word problem and write a function that's called the objective function. That's the name for it. I've written that here. And once we write the objective function, we're just going to run the procedure to find the min and max of that function. And in the case where we don't have a closed and bounded interval, we will do a couple of extra steps to determine whether there is a min or a max and how to find it. But basically, we're still performing a very similar procedure. So I've put up here. This is the procedure to solve an optimization problem. You can copy this down, screenshot it, whatever you want. And basically, this is just a summary of what I've been talking about. What you want to do is first identify the quantity to be optimized, and that's here. And then once you've identified this quantity, you want to write an objective function. You want to specifically write that quantity as a function of some other variable that you can define in the problem. This is perhaps number 3, is perhaps the only thing that's going to be a little bit different. You want to identify the domain of the function. Now I know you're going to say, wait a minute, we've identified domains of functions in the past. But in the past we were always talking about the mathematical domain of a function. Like for example, if I have f of x equals x squared, certainly all real numbers are in the domain of that function. But let's suppose that x represents the length of a piece of fence. Well, it doesn't make sense to say I have negative 5 feet of fence. So instead of talking about the mathematically possible domain, we're talking about really the realistically possible domain, what we call the feasible domain of the function. So we might define the domain of a function to be less than it is mathematically, theoretically possible to define it. And that Really just depends on the physical situation defined by the problem. So once we've done all this, once we've identified the objective function and its domain, we just use the optimization procedures that we've already learned. So very much of this section is really about reading a word problem and coming up with the correct objective function and domain. That's really mostly what this section is about.